This is clearly a very, very long way from what is actually true, and we're going to correct that a little bit in the rest of today. And in particular, the first talk after this break is by Xingliang Li, who is going to talk to us about sigma coordinates.
Thanks for the opportunity and the invitation from me. I'm going to. Can you hear me?
Good.
I'm going to introduce a new approach to implement the sigma coordinate in a numerical model for the atmosphere and the ocean. Because it's just a simple story, so we only got 4 parts. One is the motivation, then the new approach, and secondly, the associated idealized experiments, finally the conclusion. First, we goes to talk about the motivation. As we know, the numerical model becomes more and more important for the forecast and the research. And since the numerical model always uses the scalar equations, so the coordinate is the basic element of it, especially the vertical one, because it's associated with tackling the terrain. And the choice of the vertical coordinate can affect the performance of a model. That is why we choose this topic. I want to say the importance of the terrain again. If you ask the John Mallory, what do you want to include the Mount Everest in the model? He may answer that because it's there. But however, there are many other reasons. Besides the large-scale mountain makes the flow over it and flow around it, even mesoscale terrain can affect the atmosphere significantly. Here is the example. If the airflow flow over the mesoscale here, we got Li waves here, and the mountain waves propagate upstairs, and they associate cloud and the precipitation. So we can see that the multiscale terrain significantly affects the atmosphere. We should have them in the model, but how much? Here is an example. Left one is the real terrain, and we got the wave-like flow like this, and the cloud here, precipitation here. And if we smooth the terrain in a model, we will get the quasi-horizontal flow and the run pattern of the cloud as well as the precipitation. So now we make sure that the terrain significantly affects the atmosphere, and we have to include that in a model. How to do that? In a dynamic core, we always use the vertical coordinate to handle it and obtain a simple bottom boundary condition. There are 2 kinds of vertical coordinate can do this. The first one is the terrain following coordinate, that's the sigma coordinate, and the other is the step mountain coordinate. Here's the schematic view. And in the terrain following coordinate, we can handle the continuous terrain, and there's no internal boundary, but the horizontal coordinate surface is non-horizontal. And in the step mountain, we got the quasi-horizontal coordinate surface, but the inner boundary, and they can handle the discontinuous of the terrain. Until now, most atmospheric and ocean models use the terrain following coordinate. However, there are many numerical errors in the sigma coordinate. The most concerned one, I think, is the PGF gradient force errors. And we give an example of this. Black line represents sigma level. And this is the expression of the PGF in the sigma coordinate. We can see that there are 2 terms. And unfortunately, the 2 terms always have the same order of magnitude and opposite in sign near the steep terrain. So there is the error. We'll give an example of that. Assume that the analytical value of these 2 terms are 10 and 9.5. And if we calculate that as the 10.1 and 9.4, so we got the relative errors of these 2 terms are only 1%. But can you see the results? We got the relative error of the PGF 40%. That is the PGF error in the sigma coordinate. There are many methods are proposed to overcome the error. In general, there are 2 kinds, I think. First one is adjusting parameters before calculating it, and the other is design a high-order computational scheme for it. And all these methods are are designed upon the two-term computational form of PGF, and they are all designed to alleviate the errors to an acceptable level. How about we go back to see this expression in the sigma coordinate? We can see that there is only one term in the z coordinate, and there is no PGF error in this coordinate. So can we keep the computational form of PGF being 1 in the sigma coordinate? And the answer is yes, so I gave this talk here. We design a new approach to implement the sigma coordinate. Here is the second part. I want to introduce the new approach. There are 3 steps in the design: categorizing the existing methods of obtaining the scalar equations in the sigma coordinate, and then we reanalyze the reasons for inducing the PGF errors in both methods. And based on the scalar gradient expression in the curvilinear coordinate, we find that using the covariant scalar equations of the sigma coordinate, we can get the one term of computational form of PGF. Firstly, we see the categorizing. Actually, there are 2 types of method of obtaining the scalar equations of the sigma coordinate. The first one, we from the scalar equations of z coordinate to the scalar equations of the sigma coordinate by train rules. That is the special partial derivative from the z coordinate to the sigma coordinate. And the other kind, we from the vector equations of the atmosphere or ocean, and we use the basis vectors of the sigma coordinate to expand that vector equations. So we got the scalar equations of the sigma coordinate. But both methods will bring the 2-term computational form of PGF due to the different reasons. In the first one, here is the scalar gradient expression. And due to the train rules, so we got the 2 terms in the scalar gradient. And we substituted the pressure to this question, okay?
The previous slide.
This one?
What is the basis vector here?
Basis means, may I use the blackboard?
Yeah, sure.
Basis vector means, oh, that's the right one. If we got a curvilinear coordinate, there is the basis vector. Because I show that this is the basis vector of the z coordinate. But in sigma coordinate, because it's a non-orthogonal coordinate, they have two kind of basis vectors. The one is the covariant. This is covariant basis vectors. It's along the coordinate surface, and the other is the contravariant basis vectors. Yes, you know that. Orthogonal to this coordinate surface. That is, I use another color. Oh, that is like this, because this is the coordinate surface, and it's orthogonal to it, and orthogonal to this. So what I say is the basis vectors is the pair of this white one is the pair covariant basis vectors, and the red one is the contravariant basis vectors. Is that clear? Okay. So we continue. So continue to the categorizing. In the second method, there are 2 terms of computational form of PGF either, but the reason is different. We can see that when we use the covariant, this one, this black one, white one, sorry, white one. There are a summation in every direction, and unfortunately, the contravariant metric tensor in the sigma coordinate, there are 2 non-zero components. So substitute this into it, and we got the 2 terms. Then, how to keep the 1 term of computational form of PGF in a sigma coordinate? We go back to see this. This is the scalar gradient formula in a curvilinear coordinate. You can see if we use the covariant basis vector, they are always the summation. But when we use the contravariant basis vector, there's only 1 term in every direction. That is to say, if we use the contravariant basis vector of the sigma coordinate to expand the vector equation of the atmosphere, we will get the 1 term of computational form of PGF. That is what we get. Use the horizontal momentum equation as an example. The first two row is this in the new sigma method, and the last two rows is those in the classic method. We can see we got the one-term computational form of PGF in the new method, compared with the two terms in the classic one. And note that, see these equations, the forms are similar with the classic one and as well as the coordinate. So we use this similarity. We can propose, except for these terms. So we use this similarity. We can propose a unified framework to conclude the equations in the three coordinate together. How to do that? We face two problems. The first one is the difference in the form, and the second one is the different value. We design three parameters, these three, and value them differently in each coordinate. So we combine them together. And for the value, for the scalar component value, like the u, v, w, and omega, and the gravity wave, we introduce a transformation matrix, and also value the transformation matrix like this in different coordinates. So we can transform the scalar component from one coordinate to the other. Then we got the unified framework of the three coordinate. Here comes the short summary of this new method. We can see that through categorizing the existing method of obtaining the sigma coordinate and reanalyze the causes of the PGF errors, we found that it's not the sigma coordinate, but the way it is implemented that caused the well-known errors. And based on the expression of the scalar gradient in a curvilinear coordinate, we find that if we use the covariant scalar equations of the sigma coordinate, there is only one term of the computational form of PGF, which bypasses the errors completely. And as we showed last slide, a unified framework is proposed because there's similarity in the equation set, and it's, so we can use this new method in a numerical model very easily. In addition, there are the curvilinear terms and gravity terms in every momentum equation of the new method, which has to be further investigated if this has the bad effect or something else. Now here we have got the one-term computational form of PGF, but how will it really do better than the classic one? So I have done some idealized experiments. We do the idealized experiments in the vertical section, and we put a bell-shaped mountain here in the center of the domain, and we use idealized pressure field like this, and we do the discretization of the PGF in both methods using the forward scheme in the vertical and the leapfrog scheme in the horizontal. Through the idealized pressure field expression, we can calculate the analytical PGF, and use this discretization, we can calculate the computational PGF minus the analytical PGF. We got the absolute error, and divided by the analytical PGF, we got the relative errors. In the following analysis, we compare the relative errors and the absolute error of PGF in both methods, and we see the results. We have done two series of experiments. The first one is a basic comparison. The second one is the sensitive experiments. In the basic comparison, we do with and without horizontal PGF experiment. And in the sensitivity experiments, we increasing the terrain slope and as well as the horizontal resolution. So here we got 4 experiments. The first one is the non-PGF experiment, and the second one is the with PGF experiment. Third is we increasing the terrain slope, and finally we're increasing the horizontal resolution. So we describe the results of these 4 experiments one by one. Here is the results of the non-PGF experiments. We calculate the absolute error of PGF in both methods, the warm color means the positive value, and the cold color means the negative value. We can see that the right one is the absolute error of PGF in the new method. Is much less than those in the classic method. Now we analyze the results of the with PGF experiments on three aspects. Firstly, we see the pattern of the PGF. First row, here is the analytical PGF in both methods. The second row is the computational one. We compare the pattern of this. In the classic sigma method, the computational PGF, there are just one center here, but split into two centers here. And compared with this, in the new method, we got the consistent pattern of the PGF. Secondly, we compare the relative errors of the PGF in both methods. We can see that in the whole domain, the relative errors of PGF are 1 orders less than those in the classic one, as well as the root mean square error here of the whole domain. Thirdly, we pay attention to the pattern of absolute error of PGF on every sigma levels. The left figure is the slope of the sigma levels. We can see that have the peak here, and the right two one are the absolute error of PGF in both two methods. That in general they're similar, but if we pay attention to the peak position of the peak, we can see that the absolute error of PGF in the new sigma method is exactly the same pattern with the slope of the sigma levels. So that is to say, the absolute error of the PGF in the new method is much more easier to predict. Here we make sure that our new method do better than the classic one from the basic comparison. Then we see the sensitivity experiments. First is we increasing terrain slope in all the experiments from the minimum value of the slope of terrain is 30 degrees, and we increase that to 60. There are 121 experiments. We calculate the relative error of PGF in both methods. The middle one, we can see that in the classic method, the relative error increasing according to the increased terrain slope. But however, the relative error of PGF in the new method almost keeps the same according to the increasing terrain slope. Finally, we see the results of the increasing horizontal resolution experiments. Left, we also compare the absolute error and the relative errors. And the left one is the absolute error of the PGF in both methods. Here is the increasing, we increase the resolution. We can see that the red line slightly decrease according to the increasing resolution. But in the new method, the blue one, they decreased significantly, especially after this point. The right two figures are the relative errors of them. Are similar. The results are similar with the absolute error. We can see that the relative error of PGF in the new method also decreased significantly than those in the classic one. And note that in all the 800 experiments, the relative error of PGF in the new method are at least 1 orders less than those in the classic method. After we introduce the new method and have done some idealized experiments, here comes the conclusion. We propose a new approach to implement the sigma coordinate, and by reanalyze the PGF errors, and we find that use the covariant scale equations of the sigma coordinate, we can get one-term computational form of PGF in the sigma coordinate so as to bypass the errors. And in all the experiments, the relative error of PGF in our new method are at least 1 orders of magnitude less than those in the classic method. Especially in the sensitivity experiments, the PGF error in the new method decreased more significantly, both to the increased terrain slope and horizontal resolution. That's all of this talk, and hope you like it, especially where are you? Shara. Shara. That's all, thank you.
Wow, questions?
So that looks very impressive, but I think you only focus on the pressure gradient calculation. So you essentially did the coordinate transformation, if I understand that correctly, so that essentially pressure gradient calculation becomes easier and more exact. But the disadvantage is that you buy in additional curvilinear terms, so those purple things that you had underlined. Have you tried to evaluate those and essentially you can just do some similar thing, just diagnose in the two systems the different terms and look how similar they are. Did you do that? And
this is a very good question, because I have done that, but that is the topic of the next month. I'll give another talk about this. I have done a method to deal with the. I have done another approach. That is, we design the orthogonal basis vectors because now the classic sigma coordinate is non-orthogonal. You know that. I draw it like this, but we have done this, but I'll give the talk next month. So you know the time is limited.
okay.
Please.
So one of the nice properties, say with the z-coordinate model, is because you're taking estimates of the pressure gradient at the same level, if you take the curl of the equations, you get exact cancellation, and so you don't get any development of vorticity. Here, as I understand it, you're at each different level, at each different depth with your velocity points, you're estimating gradients at different depths.
Yes.
And so you don't get any cancellation between, say, the right-hand point of one calculation and the left-hand point of the neighbor, or am I missing something?
I don't know if I understand clearly of your question, but I want to say that there is a big difference between. Okay, may I go back to the slides? We see the equation. There is a big difference, I think, in my opinion. When we use a new sigma method, actually the equations are just built on this surface. But when we use there's no z-coordinate. When we use the z-coordinate or the classic method, the equations are just, I want to say that the equations is orthogonal, but actually the coordinate is not. When we use the new method, the coordinate is not non-orthogonal, and as well as our equation. So that is to say, we just describe the things totally in the sigma coordinate, but the classic method don't do this. So they have the two part. This is my plan. I don't know. Is that answer your question?
Well, I was more looking at the numerical discretization. If you take the curl of the top two equations, the V1 and the V2 equations, well, that's one equation. Take the curl of that equation, does the pressure gradient turn just into a barachronicity? Does it turn into something that looks like gradient of rho cross gradient of pressure along an appropriate surface?
You mean
in an exact way?
Yes. Actually, I give a more description of this pressure. Because we actually calculated along this surface. So you are right that what we what the results of this is not the actual pressure in the real world, but use do you remember that transformation metric? We can transform that. We can transform that from every coordinate as you like. So I think that not may be a problem. Is that what you said? I don't know.
I don't see it, but I haven't thought
Maybe
about
I not understand your question clearly. Okay, please.
We're just trying to sort this out here, but by going along the coordinate surface, now you've added a gravity term in the equation, that thing on the far right.
Yeah.
Yeah, and so, for example, if it were hydrostatic, that second term in the pressure gradient, the dP sigma, essentially would be the gravity term. That would be exactly the same as that term.
Yes, that's a
So, you know, you've still got both those terms, and now you've got the difference between your dpdx along the coordinate surface and your G1, whereas before you had that other difference, but sort of the same thing.
I think that in your opinion, we just transform the errors to other terms.
Yeah.
But in my opinion, it's not that bad because we do some dimensional analysis that these gravity terms will not have the the errors like the PGF. They're not same order of magnitude and opposite in sign. So there's no the errors of this kind.
So they have to be the same, because, I mean, suppose the pressure gradient's only horizontal. Whatever you have on the sigma surface has to be canceled by gravity, right?
But this equation is actually in the sigma coordinate, so I think that it's maybe not the problem of cancel that.
But if the PDX at constant Z is really zero, then you've got the PDX along the sigma surface, which is not zero,
Yes.
and you've got to have some other term in the equation which is exactly equal and opposite, and it's going to be that G1 term, isn't it?
So we better think about it.
Because the V1.
Otherwise it's going to move, right? If you're in a situation where you're in hydrostatic balance, you've got a hill, you have to stay still, right? So the forces have to cancel the zero. So that term that you put in there, because it's on the inclined slope, we'll see a gravity force in there, right? So that term will not be zero. And there has to be an equal and opposite term such that the net force is zero, so the system doesn't move.
I think that's the view in the Z coordinate, but might not happen in this one.
The question is, when you're evaluating this dPdx, what surfaces, you're evaluating these gradients along constant Z. That's the whole point of your talk, right?
Yes, that's along the sigma
Not along a surface,
levels.
not along.
So I think that there's no problem. Maybe I should think about it.
Sure.
Carefully. So may I keep this question and do some homework?
Oh, I see what you mean, yeah. Okay, now I understand that. Good, okay. Are there any further questions? No? Okay, so then I think we should thank you, Anne. That was